Hello, and thank you for joining me. You're here with data science teacher Brandon, and we're going to discuss how to make many different types of recurrent models, recurrent using a recurrent layer in TensorFlow. Okay, so I'm just importing kind of standard data science stuff, getting a train test split, and we're going to make just a fake data set today, so we're going to make regression. Okay, I'm also going to look at using the Plotly backend for pandas. It really just gonna help being able to see a little bit more details than just the standard pandas plot. So use pd.options.plotting.backend and just give it the Plotly string, and it will change kind of the underlying backend options, which plotting function, which engine is used to make the pandas plots. And it worked pretty well. Not perfect, but it works pretty well, and it's good for what we need today. So just to make regression, just making x and y here. Going to do the train test. But okay, what I'm going to do our first recurrent layer, we're going to do a simple RNN. This is essentially as simple as it can get for the recurrent. And I actually find this works well in many situations. If you have kind of like spreadsheet data type of thing, but it really works well where there's maybe not that level of complexity that there is with words, where something later in the sequence would have a lot to do with something that's happening now in the sequence. There isn't that kind of historical, there isn't a time series aspect. And truly, sometimes spreadsheet data there isn't that many hidden levels to it. It just is what it is. So I actually find this simple recurrent layer, it works well in a lot of situations. I've found as well for stock market predictions, it actually works quite well as well. So the really important thing is that we create the sequential model. We're going to add a recurrent layer, so layers.simple RNN. Just doing 100 units, kind of doing it equal for all of them. And we use the ALU activation function, so tf.nn.alu, so exponential linear unit. Has a nice little curl, it's like the ReLU, but it has a little curl to it, a little bit smoother, so there's a little bit of learning that could happen in the negative space. Okay, in the input shape we have here, this is really important. So this honestly was a mistake that I made. It lost a lot of time on this comma 1. Okay, so what we have here is we have X shape. We're getting the number of columns, so that dimension. But the really important thing that we have here is this comma 1, because recurrent layers, convolutions as well, they require this extra dimension, because a spreadsheet has X and Y, but you could put many spreadsheets on top of each other if you wanted to. It wouldn't make sense, right? But there's still a dimension, there's one spreadsheet in the Z dimension, and we just need to let our network know that that exists, sort of thing. So we just let them know that there's a Z dimension of 1, okay? And that's what that is right there. So the Y is kind of the batch size, the number of rows, the number of columns needs to be the same every time. And then we have a comma 1, we're saying one spreadsheet, and it's one data frame, one thing in the Z dimension, okay? And we really need that to make this to work. So really simple. I struggle with finding the comma 1 at first, but it is very important that we do this, okay? And then just we're doing regression prompts, then just our output layer, we're going to have 1 unit. My loss is MAE and my optimizer is Atom. Okay, so training this for 200 epochs, batch size 32, and then split 0.3. Okay, and I'm going to save the fit as our history so that we can then look at the history object. So we see training, not super exciting with that, but we're going to put this into pd.data frame here, history.history. So this is a dictionary, which fits very nicely into a data frame. And then because it's in the data frame, we just go dot plot, looking at the model history. And now the reason this is kind of nice and plotly is because you can actually go down and just see exactly what the values of our MAE are as we go through this. Just allows you to inspect it a little bit better. It's kind of nice. I'm going to then evaluate the train and the test set. And I'm going to save those for later. We'll look at all of them together. Okay. I'm going to do the same thing for the GRU, so the gated recurrent unit. Okay, so we have 100 here. We're going to do we try to make everything as equal as possible so that we could judge how well each one works. Okay. Then we're going to do the input shape. again, we're doing the columns, same number of columns, and then the z dimension comma 1. Okay, and output of 1, we'll do the same loss, the same optimizer, dot compile, and I'm fitting it, and I'm saving this history. Okay. And let's move over this. So you can see here it gets quite low. It gets even lower than the simple RNN. It gets quite low. GRU does really well. It's like simpler version of the LSTM. It still has some of the gated levels. Just kind of allow for that deeper memory to happen. But I find that LSTM works well. It does work well sometimes though. So it's good to try the GRU when you're trying the LSTM. It's a good experiment to do. I'm going to take the train and test MAEs for both those. For sort of the GRU, we can do the same thing here for the LSTM, just adding 100 units, ALE, and again, the split is the columns, comma 1 with the Z dimension. Okay, compile and take my LSTM train test 200 epochs, batch size of 32, and history. Okay, so very, very simple. You can see there's a lot more going on in the LSTM, and really, although this is big jumps, you would like not to see that this has to relearn, but what's happening here is that the network starts to overfit. And that is something you really have to be careful with the LSTM, is that it's a very powerful layer, and so we need to be conscious of, and we will often see overfitting happen with it. Okay? So I'm going to do the LSTM evaluate, just to try some other slightly expanded architectures for the LSTM network. So first one, just adding a dense layer. Nothing really special you need to do here. You just add a dense layer and activation of ALE. Okay, so nothing changes really in that sense. What does happen though is you'll see this. When you look at the training history, it starts to overfit very, very early. And that is something you have to be very careful with dense layers, is they really map your data, especially after an LSTM layer. They really map your data in versus being predictive instead of generalizing enough. They really learn a lot of randomness very, very quickly. Densities are very powerful with LSTMs, but you have to be very careful. And you see the extreme overfitting that we're getting here. We're able to get a very low train score, but our test score, I believe this is probably one of the worst test scores that we have, okay, in terms of the MAE. You absolutely right. So then taking the LSTM, or sorry, the train and test scores of those, I'm going to do the similar thing, but what I'm going to do here, really common, this does take a lot longer to train than is one thing to be aware of. Because essentially this has to do one extra calculation every kind of step inside the LSTM, which will take a long time, truthfully. Will add quite a bit of extra time. But this is allowed to help um, like overfitting and sort of thing like we saw in lots of the other ones. So what I'm going to do is add a dropout layer right here. This is adding a dropout layer, not after, but actually inside the LSTM. And allows really to make sure that it's not overfitting by itself. And so go through this, and it works pretty well. But you can see here, look at the training history, you can see it's just to get a little bit crazy and stuff like that. So this might work well. I would suggest this could be a really good situation, maybe a little bit less of a dropout, but something that you do for a long period of time. Because once the shaking up kind of happens, you can fall back into a better. You can see it went to a lower score here and a lower score again. It probably just needs more time to find a lower score again. It can be a little bit tricky training these, but this is something this might need a little bit more time. You can see it's, although it's not consistent, it is eventually improving overall, which is really our goal, and that's the idea of turning off some of the layers. We're going to get bad predictions sometimes. It's going to have to relearn, and it's going to have to kind of rethink about things, kind of maybe fall back down the gradient from a slightly different angle, and maybe it will work out a little bit better. It often does. Okay, and the last one we're going to talk about, a really common type of layer, a really common thing that we want to do with the LSTM is adding a bidirectional layer. So what this is going to do is going to train on the backwards propagation and the forwards propagation, right? So we're getting kind of two, essentially it's faster. Is one of the biggest things. I find it's a little bit faster, but you can actually see that it converges. We could have stopped training it a lot sooner. I did stop this one at 150 epochs when we're training it, you can actually see it converges much, much faster. And that's really the biggest thing, is that you could train it for just as long, but it's going to allow you to get to where you want to go much faster by kind of training on the forward and the backwards propagation, or sorry, allow updating to happen. Okay, and we're going to get the evaluation scores of both nodes. This is actually, sorry, I want to make sure I explain this. This is really important. So what we have here, when you're giving it the exponential, or sorry, the bidirectional layer, when we had the other layers, we could just manually put in, we're going to have this extra dimension, and it would know, it would just create it as we were going into the model. The bidirectional layer, we actually have to manually create this extra dimension as well on our data set. So pretty easy. We're going to take the square brackets. So we're not going to do anything in the first and second dimension, but in the third dimension, we're going to go numpy new axis. Then just create a comma 1. You can see that right here. It's just going to bad shader. This will show you when you run this again. This is going to be 30 comma 1, and this is going to be 30 right here in the second dimension. You can kind of see what that is. That is right there. So this is 30, and then this is 31, 30, and then 1. Apologize, it's not showing right now. That allows for the, how would you say that? That allows for the that extra dimension. You're kind of saying you're going to be an extra dimension, and we're giving our data frame, or our data frame. This is a numpy array, but we're giving it that extra dimension to start with. Okay, and so there. And when we look at all of our scores together, we have all of them with the R1s. Look at this. We have the RNN, GRU, LSTM, dense LSTM. So it's the LSTM dense layer, the dropout inside of the LSTM, and then the bidirectional LSTM mod. Okay. We can see the dropout LSTM, the bidirectional layer, and the GRU. They all did really, really well. They were able to get those scores in. Not perfect in terms of overfitting, but you can see there's very little. It's almost underfitting in some sense. We're not overfitting in an extreme sense. Maybe the GRU is starting to get 7 to 9 is getting to be a pretty decent amount. But you can see your 7 and 8. Those are both really good, and this might actually be, because we got the same scores in both of these, might be the best that we could do for both of these. Okay. Thank you very much for joining me today. You can see here really the dropout LSTM, the bidirectional LSTM, and the GRU did really well. Really recommend just the simple RNN, the LSTM are both really good by themselves. Don't take this as just the, you know, the Bible, I guess you'd say. But they can be very good in many different situations. Okay, it's good to try them all, but here in this specific case, we see what worked well and what didn't. Okay? Thank you so much for your time today, and I will see you next time.